Welcome back. Here's another synthesis example. In this example, we're going to start with bromobenzene, and what we're after at the end of the day is an ester. And so here, very clearly, we're going to have to increase the amount of carbon in our carbon skeleton. So nothing will apparently happen to this benzene ring other than the fact that we're going to end up with new substituent at this particular location. And so for sure, at some point, we're going to be requiring a carbon-carbon bond-forming reaction in order to make this particular ester. So starting with our bromobenzene, there are not many things we can do with this. We haven't been taught too many reactions where bromobenzene is our starting material. In fact, we've only looked at one particular reaction, which may prove useful in this particular example. And that is converting this bromobenzene to a corresponding Grignard reagent, an organomagnesium halide, or in this case, a phenylmagnesium bromide. And so that becomes a useful strategy for generating a carbanion. And the minute we form that carbanion, we should be thinking, this is now a good reactant reagent for carrying out a carbon-carbon bond-forming reaction. So that's where I'd like to start this particular example, is with the introduction of magnesium metal. So magnesium metal, generally in an inert solvent, something that we can dry quite well, so THF would be fine. Diethyl ether is typically used, but magnesium metal will insert itself into the carbon halogen bond to give us phenylmagnesium bromide. So we can show that it's MgBr. So this is a very good carbon nucleophile. Like organolithiums, you have carbon with basically a full negative charge. Shown here is the covalent structure, but you could show this as an ionic structure as well. So looking back or looking forward to our ester that we want to make, notice how the phenyl ring, which is where our benzene will eventually become, it is attached to the ester oxygen. And there's actually one carbon in between the phenyl ring and that ester oxygen. And you may recall that one way that we can make esters is to react an alcohol with an acid chloride. So recall that when we talked about acid chlorides reacting with alcohols in the presence of pyridine, that the R of the alcohol, the ROH, that R group ended up being what was attached to the ester oxygen. And so, in a sense, if we make an alcohol that has this structure, then we can react that alcohol with an acid chloride in the presence of pyridine to give us our final ester. And so that's one way, one convenient way of making esters, and in this case, one route that we could potentially take. Try to convert this structure to an alcohol. Now, it's not phenol, it's not a phenyl ring directly attached to an OH group. We do have a single carbon in between our phenyl ring and our corresponding oxygen. And so this is where we're going to have to at least increase the size of this molecule by one carbon. Now, there's a couple ways you could carry out this reaction. One way that we've looked at is by introducing CO2. So introducing CO2, the Grignard reagent, in this case, the phenylmagnesium bromide, is going to react with CO2 to form the corresponding carboxylate. And then in the second step, that carboxylate can be washed with dilute acid, H3O+, to form the corresponding carboxylic acid, in this case, benzoic acid. So we have our benzoic acid, and we've already talked about the fact that we would like to form an alcohol similar to this structure. So importantly, we have increased the amount of carbon in our original bromobenzene by 1 by the introduction of CO2 in this Grignard reaction. So this carbon will end up being this carbon in our final structure. So we have a carboxylic acid. We need to form an alcohol before we can react with an acid chloride to form our ester. So we need to think about reducing this carboxylic acid. And there's a couple of ways in which we can do that. But we have seen that we can use excess lithium aluminum hydride to carry out this reduction. And so that would be a reasonable strategy. So excess lithium aluminum hydride. We introduced this first in section 12 when we were talking about reduction of esters. We also showed that we can reduce carboxylic acids in a similar manner. The mechanistic details are a little bit more complex, but nonetheless, we can do so. So this is our nucleophilic addition mechanism. Again, we're not concerned with the mechanistic details or showing those on paper. We just want to come up with the most reasonable reagents to carry out those particular transformations. So in doing so, what we form is the following. We form our alcohol. So under excess conditions, we're going to reduce to the oxide, and then in final step, we'll quench with water to form our alcohol. This is called benzyl alcohol, but that's not important. But you can see now we have introduced our carbon, and this moiety, if you will, this is our ROH that we used in our ester synthesis. And so in our final step, we now need to react with an acid chloride. Now note that when it comes to the carbonyl, there's 2 carbons. There's the carbonyl carbon, and then there's an additional CH3 group as a part of this final ester. This is going to give us everything up to this point. If we cleave this bond, it's going to give us this part of the molecule. So we need to be considerate about, what type of acid chloride we need. We're going to need at least a 2-carbon acid chloride. So ethanoyl chloride will be the reagent that we need to use. So here's our ethanoyl chloride, and pyridine is used as well, because we will generate HCl with any reaction that involves the acid chloride, and the pyridine acts to form a salt with the HCl, pyridinium chloride. And so this becomes our synthetic route for this transformation. We start it with bromobenzene. We recognize that we want to form an ester. One way to form an ester is from the corresponding alcohol and an acid chloride. So we needed to set out a strategy to convert bromobenzene to the corresponding alcohol. Given that there are 1 additional carbons in this alcohol, we need to carry out a carbon-carbon bond-forming reaction. Easiest way to do that, or one straightforward way to do that, would be to convert this bromobenzene to the corresponding phenylmagnesium bromide, our Grignard reagent. We've seen in our last slides of the last lecture that this is a convenient way of taking an alkyl halide, in this case bromobenzene, but similar structure, to a Grignard, reacting with CO2, and then doing an acid wash to form the corresponding carboxylic acid. But again, more importantly, increasing the amount of carbon by 1. Once we have a carboxylic acid, there are a couple ways we can get to the ester, but again, our whole goal was not to form just an ester of this compound, but to make this the alcohol moiety or reactant that would pair well with this acid chloride to form the corresponding ester. So excess lithium aluminum hydride will do that effectively through a nucleophilic addition reaction to give us to our alcohol, and then through a nucleophilic acyl substitution, using this as our alcohol, reacting with this small acid chloride, ethanoyl chloride, we can form the ester. Now, this isn't the only way we could prepare this particular ester. One other possibility, which we can highlight here, is that we could potentially have a different route from the Grignard to the alcohol. The Grignard is a very reactive carbon nucleophile. There are various small molecule electrophiles that we could use. And in this case, we could use formaldehyde. This would be a similar strategy for increasing the amount of carbon by 1 by using the smallest aldehyde. So this carbon nucleophile reacting with this aldehyde will form the oxide, and then we follow that up with a water wash, and we end up with the corresponding alcohol. So this is another example of a nucleophilic addition reaction from our Grignard reacting with our small aldehyde, followed by a water wash, and that will generate our alcohol. So think of it as you're looking at a reaction of an aldehyde with a carbon nucleophile. One of the typical reactions is nucleophilic addition, and in that examples that we've seen previously in chapter 12, we form alcohols as a result. So either strategy would be completely acceptable in an examination or assignment type situation. They're all very reasonable pathways to the formation of the alcohol. By no means are these the only ways in which you could carry out this particular synthesis, but these are two viable methods. So again, if you have any questions about this particular synthetic route question or any additional questions that you come across in the textbook, by all means, send me a note and we can either set up an appointment or we might be able to solve it by email or messaging. Thank you.